Okay, welcome to Let's Get to the Marks. We're looking at the 2017 Biology Paper 3 multiple choice section. Let's go. It's like 25, no, 29 questions, 30 questions, something like that. Which compound has the highest boiling point? This is question 5. Well, the first question under multiple choice. If we look at the first compound, it's an alcohol, has an OH group, which means it's got hydrogen bonding. And if we look at all the other three, none of them have hydrogen bonding. Okay, so A is going to have the highest boiling point. Which is the correct order of melting points in the period 3 elements? Now, the metal elements in period 3, the melting point increases as they have more delocalized electrons, so their melting point increases as we go across the period. However, with non-metals, they normally go down. They normally decrease. These are all non-metal elements. Now, it's a bit unusual. The general pattern is a decrease in melting point. However, we've got an exception here, which is sulfur, which is going to skip the pattern. And the reason being is sulfur structure is slightly different than phosphorus. So if we were just following the general pattern that across the period the non-metals decrease in melting point, that would be normal. However, sulfur kind of like changes the pattern. So you see like sulfur is group 6, phosphorus group 5, then it goes group 7, then group 8. So generally as we go across, melting points decrease. However, sulfur has a structure where it forms a ring of 8 atoms. So it has the largest van der Waals forces out of all these non-metals. Okay, question 7. Which of these is not a correct statement? Transition metals form colored ions. Yep, that's true. So that's not our answer. Variable oxidation states. Yes, they do have variable oxidation states like iron, Fe2 plus, Fe3 plus. A ligand accepts a pair of electrons from a transition metal. No, a ligand does not accept a pair of electrons from a transition metal. Ligands donate electrons to the transition metal. So C is not a correct statement. Right. The table shows the possible conditions and products for the cracking of alkanes, which is correct. So you just got to look at all of these. The one that's actually correct, the type of cracking is catalytic cracking. It has a slight pressure and high temperature, and you get a lot of branch chain alkanes and aromatics. You just have to know that. Okay, 2,4,6 trichloropheno, a weak monoprotic acid with a Ka of 2.51 times 10 to the minus whatever that is, 3, at 298 K. And we've also got the concentration of hydrogen ions. Well, you need to rearrange the equation for Ka, which is products over reactants equals the Ka. Now, when we simplify this, this would be H plus times A minus. However, we know that A minus and H plus are equal, so we do H plus squared over HA, which is the reactant, the acid that's dissociating, equals Ka. So they have given us the hydrogen ion concentration. Oh no, they want the concentration of hydrogen ions. So we need to rearrange this equation so that we do the square root of HA times Ka. And they're giving us the Ka and the HA. So you just want to square root HA times the Ka, and they've given you the HA and they've given you the Ka. And you just square root the multiplication of those and you'll get the hydrogen ions. And it is 7.09 times 10 to the minus 4. Now that's really small and my eyesight's bad on this screen. Question 10. What is the pH of 0.46 mole per decimeter solution of potassium hydroxide at 298 K? Well, we've got the Kw here, so we want the Kw equation. Kw equals the concentration of hydrogen ions times the OH minus ions. We're asked to find a pH, so we need the hydrogen ion concentration. So we need to rearrange that equation. So Kw is hydrogen ion concentration is equal to Kw over OH minus. Okay, and we do that by dividing both sides by OH minus. And now we just plug in the numbers. So 1 times 10 to the minus 14 is your Kw, and 0.46 is your OH minus ions. Because it's a strong alkali, potassium hydroxide fully dissociates, so the concentration of the alkali is equal to the OH minus ions. And then we get 2.17 times 10 to the minus 14. We just minus log the answer, remember. Once you've got the hydrogen ion concentration, minus log the answer, and you will get the pH, which is 13.66. What is the mass in milligrams of carbon formed when 3 times 10 to the minus 3 moles of propene undergoes incomplete combustion? Hokey dokey dokey. Well, first things first, we have the moles, then we use the ratio of propene to carbon. We know it's 2 to 6, so we need to times this by 3 because that's the same as 1 to 3, 2 to 6. So we actually have, if we have that many moles of propene, we're going to form 9 times 10 to the minus 3 moles of carbon. Now let's turn that into grams. So we times moles by mR to get grams. It's 0.108 grams. Then we go, aha, it wanted it in milligrams. So we need to times by 1,000 to convert the grams into milligrams. And we get 1.08 times 10 to the power of 2. Beautiful. Let's move on. Question 12. Which compound gives this infrared spectrum? Okay, so you've got this here. You'd look this up in your data book, and this would be 1750, which is a carbonyl group, the C double bond O. And you've got one bromobutane that doesn't contain that bond. You've got butan 1O, alcohol doesn't contain the bond. You've got butanal, which does contain that bond. So the answer is C. Which pair of compounds does not form a racemic mixture when the compounds react? Right. To get a racemic mixture, you need to have a chiral compound. You normally need a planar bond as well. So that it can be attacked by the species either side of the bond. But basically, let's just go through first of all and see if there's one here without a chiral compound, without a chiral carbon, then it's not going to form a racemic mixture. So we just need to check, is there a chiral carbon in the products? So when you do HCl, yeah, we can see that's going to form a carbon compound, a compound with a chiral carbon. Oh my gosh, I can't speak. B, right, we checked that out. That also forms a chiral carbon. Can you spot it? It's here what I'm circling in red. On both of those, that would be a chiral carbon, a carbon atom with 4 different groups attached. Now let's check out C. Now, if hydrogen chloride adds across the double bond here, we're also going to get another chiral carbon. Okay, so again, A, B, and C can form a racemic mixture. Now, when we look at D, D does not have a chiral carbon attached. Even when it the nitrile adds, so it becomes a hydroxynitrile, it's actually got 2 methyl groups either side of the central carbon. So actually, there's no chiral carbon. That cannot form a racemic mixture. Bada bada bing. Right, the answer's D. Okay, let's move on. Question 14. The reaction sequence shows how CH3 ethane can be converted into BrCH2 CH2Br. Okay, so we got like 1,2-dibroma ethane. So they've started off here by adding chlorine, but only one of the chlorine atoms adds. That means it must be free radical substitution with ultraviolet light. Then we've got sodium hydroxide. Well, we've got a hydroxide ion must be adding on, and that hydroxide ion has a lone pair of electrons. It's going to attack the slightly positive carbon on that polar bond of the carbon Cl bond, and so you can tell that is nucleophilic, but it's going to swap the place because the chlorine's going to leave. So it's going to be nucleophilic substitution. So our answer is going to be B, but if you look at C, it's being eliminated down to ethene, and then the ethene in step D is having the bromine added across the double bond, so it's electrophilic addition. Right. Question 15. Cisplatin is an anti-cancer drug. Which structure represents a stereoisomer of cisplatin? Cisplatin has a cis isomer and a trans isomer. So cisplatin is the cis isomer, and we're looking at B here, which is the trans isomer, where it has the same groups on opposite sides. Okay, let's look at the next one. The diagram shows the Maxwell-Boltzmann distribution of molecular energies in a gas at 2 different temperatures, and our higher temperature is the one that has shifted to the right, same number of molecules, but we've got a greater proportion with higher energy above the activation energy. And it's asking us, we can cancel out A and B because that would be the colder temperature. C and D are part of the higher temperature, and the answer is going to be D, which is slightly to the right of the highest temperature, and that's the most probable energy. Okay, V2O5, what's that? Vanadium pentaoxide can be used as a catalyst in the contact process. Which of these steps in the contact process is which vanadium is oxidized? You just kind of have to know this. But essentially, It can't be that. That's reduction, right? It's gaining electrons. So we go +4 to +5 over here. Okay, so that is oxidized. It could be B. And then we look here at C, and that is going from +4, the vanadium, to +5. So it's losing electrons. So that is oxidized. And you just have to know that the vanadium is reoxidized by joining with oxygen. So the answer is C. So in the contact process, the vanadium gets reoxidized. So first of all, it's reduced, and then it gets reoxidized with oxygen. And you just got to know your contact process, and then you'll know that step. All right, let's move on. Question 18. The structure shows a section of a polymer chain formed from the random polymerization of two different isomers. Which pair of monomers could produce this polymer? Okay, this is a little bit difficult. I'm going to start at the bottom with D, and I'm going to go through and we're going to look at trying to portion these up. So you see with D here, we could have CH2. Oh, no, let's start. Where are we? Okay, so with D, we could have CF3 and CHF. Yeah, so that could be D, the one I've done in black brackets there. Then the one in the pink brackets here would have to be the next monomer, and that is can't be ethene because, yeah, doesn't match those two monomers. So let's check C. Okay, so the C is saying it's got an ethene molecule, and then it's got this other one. So let's highlight the one I'm underlining here in pink. That would be its monomer there. Now in the green, that doesn't look like ethene. It's got a fluorine atom, so it can't be C because those two monomers don't match up. So now let's look at B. So B again is saying there should be an ethene molecule present and a CHF CHCF3. So let's do the one in green. Let's make CHF CHCF3, and you can see I can do that there. So that's okay. And then first of all, I go, hold on a minute. The molecule next door is also ethene. So B looks like our answer. Look, it looks like our answer. However, when we try to repeat this molecule again, we get the same CFH, CF3CH. But look what happens. The next molecule doesn't match either of our two monomers. So that doesn't match either of the two monomers, and so is incorrect. So the repeat units have to be the same going all the way along there. Now, if we look at this last one, so I'm going to just highlight in orange, that's this one I'm circling here. That monomer would form that part. And then this pink part, yep, that would go with that. And then we can just repeat it. Look, this is another pink one again. So it's that monomer. And then it goes to the orange one that I've circled in orange. And you can see these match perfectly. That's another orange and then a pink. So they match perfectly with those two monomers. So the answer is A. That was a bit long. 19. The equation for the reaction between zinc and hydrochloric acid is Zn plus 2HCl goes to ZnCl2 plus H2. What is the minimum mass in milligrams of zinc, 65.4 Ar, needed to react with 50 centimeter cubes of 1.68 mole per decimeter hydrochloric acid? So the first thing is we've been given the volume and concentration of the hydrochloric acid. So let's go ahead and work out the moles of hydrochloric acid we're dealing with. So 50 divided by 1,000 to get into decimeters times 1.68, and we're going to get the moles because we're doing moles equals volume times concentration here. And we get 0.084 moles of HCl. Now we want to know the minimum mass in micrograms of zinc. So I've got to find the moles of zinc. Now we're going to divide by 2 because of the ratio is 2 to 1 of hydrochloric acid to zinc. And we're going to get 0.042 N zinc. Now we just need to times that by the AR. Remember, mass is equal to MR times moles or AR times moles. So we're going to do 0.042 times 65.4. And that's going to give us our mass of zinc. Now here's where you could make a mistake. You might think it's A. Ta-da! However, we have to turn this into micrograms in the question. Milligrams, sorry, not micrograms. That's the crazy upside down U symbol. Milligrams. So I need to times by 1,000. So the answer is actually 2.75 times 10 to the power of 2. Lovely. Let's move on. 20. An equilibrium mixture is prepared in a container of a fixed volume. We've got carbon monoxide plus chlorine equals some old molecule there. It's an exothermic reaction because we can see negative 108. Whoa, what happened there? The temperature of this mixture is decreased and the mixture is allowed to reach a new equilibrium. Which is greater for the new equilibrium? Okay, so does the mole fraction of carbon monoxide go up? Does the partial pressure of chlorine go up? Does the total pressure of the mixture go up? Or does the value of the equilibrium constant Kp go up? Well, if we decrease the temperature, what happens to using Le Chatelier's principle, what happens in an exothermic reaction if you decrease the temperature? Well, if you decrease the temperature, the equilibrium is going to shift to the right, to the forward direction, because it's trying to counter the change. It's trying to warm it up. And we know that Kp is products over reactants, just like Kc is, or Ka, products over reactants. So you're going to get more product or a higher yield of product by decreasing the temperature in an exothermic reaction because it's going to shift to the right. And if that number gets bigger above, then Kp is also going to go up. So reducing the temperature in an exothermic reaction for a gas reaction is going to increase Kp. Da-da-da-da. Yeah, if you do 10 over 2, you get 5. If you do 20 over 2, you get 10, and that's why Kp goes up. Okay, 21. In a concentrated alkali, propanone reacts with hydroxide ions to form an equilibrium mixture as shown. So we've got an equilibrium mixture, which curly arrow should not appear in this mechanism. Okay, well, yeah, the first one's good. That's the formation. This one looks a bit dodgy. The carbonyl compound doesn't normally donate an electron to form a double bond. Normally, the pair of electrons go to the oxygen. As we can see in the right-hand molecule, oxygen has a minus on it. So actually, D's the correct and C's correct. All of these are correct except for B, which is incorrect. Okay. 22. The diagram shows a pH curve produced by adding a strong alkali to a weak acid. Which point on the curve represents a solution that can act as a buffer? Remember, a buffer needs loads of weak acid and it needs lots of salt of the weak. Okay, let's move on to 23. Which alcohol could not be produced by the reduction of an aldehyde and a ketone? So you've got to remember that if you reduce an aldehyde, you make a primary alcohol. If you reduce a ketone, you make a secondary alcohol. You cannot reduce one of these to make a tertiary alcohol. So essentially, if there is a tertiary alcohol lurking in answers A, B, C, and D, then that cannot be made by reducing an aldehyde or ketone. So straight away, you should be able to spot B is going to be the tertiary alcohol because it's got a methyl group and a hydroxide group, an alcohol group coming off of the same carbon, which means that it's going to have no hydrogens attached to the carbon in the middle there. That is a tertiary alcohol. The hydroxide group, the carbon it's attached to, has no hydrogens attached. Tertiary alcohol. That cannot be formed by reduction of aldehydes or ketones. Which compound does not show stereoisomerism? Stereoisomerism, obviously, we can have EZ isomerism. We can have those mirror images, enantiomers, these, the mirror images, the ones with a chiral carbon. So we're on the lookout here for, can you do EZ? Do you have 4 different groups or different groups attached on either side of a double bond? Where you have different groups on each carbon on the double bond, that gives you EZ, or have we got a chiral carbon? So here we can see I've got chlorine attached. We can see, there we go, that can do EZ isomerism because it's got that ethyl group on the bottom of that one. B, we've got 1,2-dichloropropane, and that's got a chiral carbon there. So that one in red is a chiral carbon. That's going to be able to form mirror images. So let's do stereoisomerism henceforth. Look at C, 1,3-dichloropropene. So we got chlorine off of the first double bond. And what we will see here, that can do EZ isomerism. You can see with the double bond across there. It's got different groups attached to each carbon in the double bond. Okay, so the final one, 1,3-dichloropropane, you're not going to have a chiral. It doesn't have a double bond, so it can't do EZ, and it has no chiral carbon, no double bond. So that's the one that cannot do a stereoisomer. Right, 25. Which compound can form a polymer without needing any other reagent? So we're really looking for a monomer here that has 2 different functional groups at its ends. You know, like amino acids, they can bind to themselves because they got an amine and a carboxylic acid group at the end. So we're looking for something like that with two different groups, so it can do a condensation reaction with itself. Obviously, the first one has got identical groups, alcohol groups. The second one is a dioic acid or dicarboxylic acid. That can't do it. The last one has a carboxylic group, and then it has a group that can't be involved in a condensation reaction there. And then C is our answer. It has a hydroxy or alcohol on one end, and then it has that like an acyl chloride at the end, which is basically like a carboxylic acid. So what can happen here is the hydrogen on the alcohol can go there. That is actually not supposed to be carboxylic acid. That's supposed to be an alcohol, but you get the idea. HCl can come off of there. That's incorrect there. That shouldn't have a carbonyl group, but I'm moving on. I'm trying to get through this fast. So 26, a solution of lead 2 chloride, MR278.2, contains 1.08 grams of lead chloride in 100 centimeter cube of the solution. In this solution, the lead 2 chloride is fully dissociated into ions. What is the concentration of chloride ions in this solution? So first of all, we need to look at the information we've been given. We've got the MR of lead chloride and we've got the mass. So let's do mass over MR equals moles, and we get 3.88 times 10 to the minus 3 moles of PbCl2. Now it says it's in 100 centimeters of solution, okay, and it fully dissociates. So we've also been given the volume. So now I want to divide the volume by 1,000, and 100 centimeters is 0.1 mole, 1 decimeters. And we now want to take the moles, which is 3.88 times 10 to the minus 3, divide it by the volume of 0.1 decimeters, and that's going to give us C, which is the concentration. So we're now using our second mole calculation, N over CV, and that is going to give us our moles. However, that's going to give us our concentration of lead chloride in the solution. However, remember there's a ratio of lead chloride to chloride ions, because each PbCl2, when it dissociates, will release 2 chloride ions. So we've actually got to times our answer, our final answer, by 2, because there's going to be double the concentration of chloride ions than there is of lead chloride. So double it by 2, you're going to get 7.76 times 10 to the minus 2 mole per decimeter. Right, 27, the rate equation for the acid catalyzed reaction between iodine and propanone is red equals K hydrogen ion concentration times propanone. The rate of reaction was measured for a mixture of iodine, propanone, sulfuric acid, pH 0.70. Notice there's no iodine in the rate equation, so we don't need to worry about that. It says propanone and iodine were unchanged, so we don't need to worry about the propanone. When they did change the concentration, the rate fell by a quarter. Well, we can tell, first of all, let's work out what the initial hydrogen ion concentration must have been. So what we're going to do is 10 to the minus 0.70 to turn the pH into the hydrogen ions. So the hydrogen ions initially were 0.2 mole per decimeter. That was the hydrogen ion concentration. Now we know they're first order because there's no number outside the square brackets in the rate equation. So they're first order. So if you've quartered the rate, it must be because you quartered the hydrogen ion concentration. It has like a directly proportional relationship to rate when it's first order. So after it's been quartered, it must be 0.05 moles of a hydrogen ion concentration. And all we need to do is turn that back into pH to find what the new pH is. So we minus log 0.05. And if you do that, you're going to get 1.30. Ta-da! A solution of lead 2 chloride. We just done that one. uh, oh my gosh, 385 centimeter cube sample of carbon dioxide at 100 kPa, 25 degrees, was mixed with 2.89 times 10 to the minus 2 moles of argon. The gas constant is 8.31. Geez, now what's wrong with me? Right, we need to rearrange this. So this is going to be PV equals nRT, divide by RT, PV, and you'll get the moles. So we want to do 385 times 10 to the minus 6 to change the centimeter cubed into meters cubed, times by 100,000. Because it should be in pascals, divide by 8.3 times 298 because we add 273 to 25 to put into Kelvin, and we get 0.0155 moles. Now, what is the total moles of gas? The total moles of gas is 0.044 because we add the argon to the moles we've just worked out, which is the carbon dioxide. And then we want to find out what fraction of the total moles is the carbon dioxide. So we go 0.0155, which is the moles of carbon dioxide, divided by 0.044, and we get 0.348. And the answer is A. Question 29. How many peaks does the compound have in its C13 spectrum or carbon 13 spectrum? So you're looking at how many carbons are completely different than the others in terms of the groups that are attached to them. And actually, when you look at this one, C1 and C2 at first might look the same, but C1's got the sulfur atom a lot closer than C2, so they're completely different. C3, C4, completely different again. Look where the sulfur atom is, so the groups aren't the same attached. Then if we look at C5 and C6 over here, yep, and then C7 and C8, they're all completely different. The groups are not, because it's not a symmetrical molecule, none of them are attached in the same way. So there's 8 different carbons. So there'll be 8 peaks in a C13 spectrum. Right, let's move on to question 30. A student is provided with 5 centimeter cubed of 1 mole per decimeter ammonia solution. The student was asked to prepare an ammonia solution with a concentration of 0.05 mole per decimeter. What volume of water should the student add? So we're going to really have to use our mole calculations here. And you can see, first of all, they've told us there's 5 centimeters of 1 mole per decimeter ammonia solution. So we've been given volume and concentration. So let's work out the moles of ammonia to start with. N over C times V. What have we got to do with 5? We've got to divide it by 1,000 to turn it into decimeters. So 5 divided by 1,000. And then we need to multiply that by 1. And that will give us our moles of ammonia solution. And then we want to alter that solution to make a concentration of 0.05. So how much water should we add? Well, first of all, let's work out the moles of ammonia. So 5 over 1,000 times 1 equals 0.005, and that is the moles of ammonia. Now we're told if we need a concentration of 0.05 moles, what would be the volume to add? So we've already got the moles, 0.005, and we're going to divide that by the concentration, our concentration we're trying to get to. So that's going to be 0.05. And that will give us our volume that is required, and that equals 0.1. And remember that volume is in decimeters. So as our volume is in decimeters, and all of the answers on the left over here, A, B, C, and D, are all in centimeter cubed, to find the correct answer, I need to convert my 0.1 decimeters back into centimeters. So I'm going to times by 1,000, and we're going to get 100 centimeter cubed. The answer is C. Okay, let's look at question 31. A solution absorbs light with wavelengths corresponding to red, yellow, and green. So if something is absorbing red, yellow, and green, you know from key stage 3, it's not going to look red, yellow, and green because they're going away. So what color is bouncing off? Well, if red, yellow, and green are being absorbed, it sounds to reason that the blue light is being reflected. Okay, and if blue light is being reflected, which of these ions has a blue color? Well, we've got dichromate ions there, they're orange. We've got Fe2 plus, they're normally green. Fe3 plus, normally brown. If you think of, anyway, and Cu2 plus, what kind of color ions the Cu2 plus normally copper ions come out with? Well, copper 2 plus ions are often green. Think of copper sulfate solution and its color. So, sorry, are often blue, aren't they? Copper sulfate solution's blue. So really our answer is D. That's the blue one. The chromate ions are going to be orange, and we're not going to get an orange color reflected because it's absorbing yellow and red. So the answer is D, which is copper ions. Okay. We're going to move on now. Oh my gosh, D in GCSE art as well as a D being the correct answer. Look at that drawing. Disgusting. Okay, question 32. Getting towards the end now. A reaction is exothermic, gives out energy, and has a negative entropy change. Which statement is correct? You just have to look up your entropy and know when reactions are feasible. The reaction is always feasible. The reaction is feasible above a certain temperature. The reaction is feasible below a certain temperature. The reaction is never feasible. Well, the answer is A or C. So if you have a negative entropy change, the reaction is still feasible, but it must be below a certain temperature. And finally, is this the last question? It might be. Phenylethanone can be prepared by the reaction between ethanoyl chloride and benzene. Ethanol chloride in this reaction is on the left. There's the benzene next to it. And then on the other side of the arrow, we got the phenylethanone and hydrochloric acid. So they have given us the mass of ethanol chloride, and they've given us the MR and the mass of ethanol chloride. Now, the mass is in kilograms. Okay. And they want us to work out the actual mass of grams. They've given us percentage yield, so we need to use the percentage yield calculation. Remember, yield is actual mass over theoretical maximum mass times 100. So we need to work out the actual mass. We can calculate the theoretical mass by working out the moles of ethanoyl chloride, which is in a one-to-one relationship with the product, the phenylethanone, and therefore we'll know how much we should make, the theoretical mass. We can bung it into our calculation, rearrange, and find the actual mass. So let's use the MR of 78.5 and the mass of 5.7 times 10 to the, oh, we need to change that. That's in kilograms. So the first thing I want to do is change my mass into grams. So let's go ahead and get that done. Operating super slowly at the moment. 5.7 times 10. That's to the minus 2, and that is kilograms. So we want to times that by 1,000 to get into grams. And then I want to divide that by the MR, because mass over MR equals moles. So we're going to get 78.5. We're going to divide that and we're going to get the moles. And then we know, I think it's 0.726. It looks like it is. No, 0, yeah, 0. Blimey, I can't even read off my calculator. 0.726 moles. Now that is, we've just worked out the moles of the reactant, but as it's a one-to-one reaction, we now know how many moles of phenylethanone we've got, 0.726 moles of phenylethanone. So what we need to do is multiply that by the MR of phenylethanone to get the mass. So moles times MR will give us the mass of phenylethanone, and that will be the predicted theoretical mass, how much we should have made. So 0.726 of phenylethanone times its MR, which is C6H5, COCH3. And if you add that all up, that's going to become 120. So you times 0.726 by 120. So don't forget to hit the like, subscribe to the channel. I'm going to be doing loads more videos and every exam paper walkthrough. So make sure you keep notified, because I'm trying to release a video twice a week. All right, nice one, guys. So we now get the moles, which is, what am I on about? Yeah, so 120 times 0.726 equals 87.12 grams. That's our theoretical maximum mass. We don't know what the actual mass is, so we need to rearrange. I need to get rid of the 100 on the right. I can do that by changing the 62% yield to 0.62, get rid of the 100. So the yield is actually 0.62. And so I can just do 0.62 times 87.12, and that is going to give me the actual mass achieved. And if you do 0.62 times 87.12, you're going to find out that it's 54 grams. And that answer will be B. Okay, I think that's it, which is pretty good because I've got to run out. So that should be it. Nice. Oh, one more question. Jeez Louise. Okie dokie. 130 centimeter cubed of oxygen and 40 centimeter cubed of nitrogen, each at 298 K, 100 kilopascals, were placed into an evacuated flask of volume 0.5 decimeters. Now we've got standard pressure and temperature. So at this point, yeah, we've got moles are all equivalent. Volumes of the gases are equivalent to their moles. Anyway, so we can find out like the mole fraction and times it by the total pressure, times it by 100. So we're going to do 130 plus 40 equals 170 divided by 1,000 to get 0.17 decimeters as a volume. Now I can This is basically equivalent to moles. So I can do 0.17 over 0.5 gets me 0.34, which is my fraction, times it by 100,000 kilopascals, and the answer is 34 kilopascals. All right, guys, signing out. Let's get to the marks.
You're still here? It's over.